So, a couple housekeeping things I want to mention before we get going. So, we've got that kind of final problem set. So, we covered all the panel data stuff last week. So, we kind of did a pretty good start. I think it's the first 6 questions related to that. The remaining 4 questions will be what we kind of cover this week, which is going to be instrumental variables. So, we should get through a pretty good chunk of this here today. A little bit less material than maybe some of the other topics we've covered. So Thursday's class, I'm envisioning we probably finish up or look at different examples and probably have a little bit of time to kind of start doing some review. So I've got both those practice exams up there. Only one of the answer keys is up there. So I think what I'm going to do, I know what I'm going to do, is on Thursday's class, we'll start reviewing some of those problems on that second practice exam, so practice exam B. I'll probably, to keep the class cohesive, start with some of the instrumental variable stuff, kind of reviewing that. Now, I say it'll be review, we'll have covered it today in the first half of class tomorrow. And then I'll post kind of an initial review video to replace next Tuesday's class. So we won't have class next Tuesday. I've got some things that kind of keep me away from the university. So I'll put up a video where I work through some of those review problems on that practice exam A. And then Thursday's class next week, I'll kind of continue to review, primarily focusing on exam B. So that answer key won't be up there. You'll have to kind of be in class Thursday, this week and next week to kind of get some of those answers. Okay. So those, come Thursday, even if we don't just work on instrumental variables, we can look at some old stuff as well. And then next Thursday, they'll primarily be review days. Okay. And we'll focus mostly on practice exam B, but if you have questions on practice exam A, you can bring those as well and we'll work on them. Once we kind of go through that, I'll get up an answer key to practice exam B, but I'm going to add some stuff in class that's likely not going to be on the answer key that'll be very helpful. I wrote the final, so I know that it'll be helpful. Okay. And then our final is what? Thursday of exam week. I'll get up the location that we'll be in. I just got those last night. I forget what it is off the top of my head. So I'll get that posted to Canvas and kind of mention it in class Thursday and next Thursday as well, just so kind of we're all clear exactly where that's at. And I'll kind of post the times in the syllabus. I think is that one 2:40 to 12:40 to 2:40, I believe, on that Thursday. It's in the syllabus. I'm trying to do this from memory. And that's kind of a roadmap for where we're going. So the only thing really left is we're going to have some in-class quizzes this week. And then kind of that 6th and final problem set, which is due at the end of the day. What do I have this set to be? So is this next Thursday, right? So I will try. I think there's about half of you, the problem set 5 is graded. I'm hoping to get through all of those tomorrow. So you should have that 5th problem set. I'll get the solution file posted tomorrow as well. So if you're kind of thinking about studying, those practice exams are good. But going back through those old quizzes and practice problems, and then going back through the old assignments, even though you're not going to use Stata, right? You're going to have to be expected to evaluate Stata output. And so reviewing those problem sets wouldn't be a bad idea either. Okay. So I've given you the solutions file. You can kind of run the code, see what the Stata output is, and kind of look at what the correct answer should have been. That could be expected on the final exam, right? Evaluating the output you would have seen from Stata. Okay. Any other questions for me before we kind of start with this last and final topic? Okay. So I've got the slides up there. Pretty quickly, probably jump into that do file, but we'll get started here. So what we're going to talk about, and I think I alluded to this last week, but we have a lot of issues that sometimes we can't resolve. So sometimes it's like this simultaneous causality. A lot of the times I'll kind of paint this in the context of probably the thing we've talked about the most, which is omitted variable bias. So sometimes we know that we need information on a certain variable that we don't have. Okay. But we actually have ways to get around that without using fixed effects. So even if I don't have panel data, I can solve for this omitted variable problem using what we call an instrumental variable. Okay. So kind of the setup that we have, right, is we have all these issues. And one I didn't mention, but we've talked about is measurement error. You can also kind of solve that issue with an instrumental variable. Okay. So some of the terms that I'm going to start using is this idea of endogenous and exogenous. Okay. So what we need for a good instrumental variable is something that's going to be, we say, is endogenous to our error type. right? So it needs to be correlated with the error term that we're getting from our initial regression. Okay? And then we want it to be exogenous with the things that, sorry, I'm setting this up. It would be endogenous if it's correlated with the error term. We would call it exogenous if it's not correlated with the error term, right? So exogenous means outside of our model, it's not correlated with the predictions we're making, right? Those errors that are involved in our predictions. It's endogenous if it is, right, impacting our Y variable or it is correlated with our error. This idea of exogeneity is it's not related to our predictions for Y. That might be a good way to think about it. It's not quite technically correct, but for now it's okay. And then it's endogenous if it is kind of correlated with those predictions we're making for Y or kind of what we're missing in that error term. Okay? So we're going to have two conditions for a good instrument, right? The first is what we call kind of the endogeneity condition. So this is going to be, we're using some instrument Z, right? It's not currently in our regression. It needs to be correlated with the X variable we want to find the causal effect of. And I'll write this out here in a second to kind of paint this in the picture of what we've been talking about. And then the second kind of condition we have is we need this instrument to be exogenous, right? So it needs to not be correlated with our Y variable, or technically we need it not to be correlated with those errors, right? That are kind of incorporated into those actual Y values we see. Okay. So maybe another way of thinking about this is if I'm trying to predict Y and I've got kind of this just general kind of linear regression. I know that there's some other variable Z, right, that I could hopefully or potentially use as an instrument. So what I need to be the case is that whatever these X and Y variables are, I need it to be endogenous to that X variable. Okay? Or I need that covariance or the correlation between X and Z, my instrument, to be something other than 0. Now, the second condition I need is that I need it to be exogenous to that Y variable I'm trying to predict, right? Ultimately, what I want is an estimate for beta 1 that has no bias in it, right? Doesn't have limited variable bias, measurement error bias, any of the bias that we might any of the bias that we might kind of see be incorporated into our causal effect estimate. So being exogenous to Y, right, you can think of it as the covariance between Z and Y is equal to 0. Now, more technically, it's the covariance between Z and our error term is equal to 0, because it's really hard to find a good instrument if I don't control for anything else. Right? But by saying that it is correlated with the error term and not the actual Y values, as I start to include additional controls, I'm removing things from the error. So if I remove things from the error, do you think it's more or less likely this instrument is correlated with that error? So if there's 50 things in my error term, my instrument is likely going to be correlated with one of them, right? I need it not to be, okay? If I include 49 of those 50 additional controls, well, now it only needs to not be correlated with the one thing in that error term. So as I include additional controls, this condition is more likely to be met. Because I'm taking things out of the error, it's less likely that instrument is going to be correlated with that error. If I have 50 things involved in that error that I'm not controlling for, all causing limited variable bias, well, my instrument is likely going to be correlated with one of them, right? So one way that we can kind of make sure this condition is met, or would make it more likely our second condition is met, is if we add in more controls, because that removes things from our error and makes it less likely that instrument will be correlated with things in our error. These are our two conditions that we need to have being met in order for this to be a good instrument. And I'll go through some examples that will make this a little more. So here we're just kind of setting up the theoretical kind of model. Okay. So if we kind of come back here, I said, you know, instead of initially thinking about it being correlated with the error, it's okay if you think about it as it's not correlated with our y values, holding constant that x variable we've included. So what does this kind of look like? So what we're going to do, the process for how we will kind of use this instrument is, I said that the instrument needs to be correlated with x, right? It needs to be endogenous to that x variable we want to try to get the causal effect estimate for, right? Or the x variable had beta 1 associated with it. So I know that x, if this is a good instrument, z should be correlated with it or should help me make predictions about what that x value is. Okay? So we're going to run what we call kind of this first stage where I kind of try to predict x using my instrument, or essentially I run this regression. Now here I'm just using pi instead of beta to kind of represent what the coefficients are from this first stage. I'm then going to kind of use the predictions for x using this instrument and my estimated coefficients, just like what we come up with from a regular regression. Once I run the regression, we could use theta, or we could use the kind of actual kind of x values to predict what the y values are. That's all I'm doing here. It's just y is x and x is z. I'm just kind of writing this in a slightly different notation. Now, once we have those estimates for what x should be based off of our instrument, we're then going to run the original regression we were interested in, trying to predict y using that original x variable we wanted to know the effect of. But instead of using the actual x values, we'll use the predicted x values that came from our first stage regression, right? Where we predicted x just using the values of our instrument, z. So the final kind of the final second stage regression, we won't be using the actual x values. We'll be using our predicted x values that came from our first stage regression results. Once again, we'll kind of do this in state. I think it'll kind of help solidify this idea. If we do this, the estimate we get from this second stage regression that's associated with the x variable we are interested in should be unbiased. It should remove the omitted variable bias, measurement bias, or simultaneous causality bias. Okay. So this is going to be a kind of what we call our two-stage least squares. We've got our first stage. I run the regression of x, predicting it using y, save those predictions. I then run my second stage regression where I kind of try to predict y using those predicted values of x that came from my first stage. Okay. So a little bit of kind of support behind why this happens. I'll show you one way first, and I've got another way that a little more complicated, but I think will kind of help solidify this idea. So let's say I'm looking at kind of my original regression that I was interested in. I don't have an instrument yet. If I just kind of think about how is that instrument z going to be correlated with both sides of this equation, I could think about this as the covariance of y with z, my instrument, should be kind of equal here to the covariance of, well, if it's correlated with y, this is the equation I had for y. I'm just plugging that in. So I kind of think about, okay, what's the covariance of my intercept with the instrument? What's the covariance of beta 1x with my instrument? And what's the covariance of my error term with that instrument? So I can kind of break this down into those three components. What should the instrument's covariance with the intercept be? I mean, the intercept is a value. So as z changes, is that value changing? No. So that covariance should just be 0. Right? Now, the covariance between x and z is going to be something, right? If that first condition is met, we said the instrument should be endogenous to x, should be correlated. So that's going to be some value. Right now, we don't know what it is, but it's going to be something that's other than 0. So if I think about, okay, what would give me just this middle component left if the covariance of my instrument with the error term is equal to 0, this drops out, okay? In which case, I could rewrite, right? This is a constant, so it just gets pulled out front. This would be what I'm left with. Now, if I kind of rearrange this equation, what I end up with is this estimate for beta 1 will be the covariance between y and my instrument divided by the covariance between x and my instrument. Okay? So this is where technically it's not that the covariance of the instrument and y is equal to 0. It's the covariance and the error term. Right? So that's a little bit more important. We're talking about not just the idea, but the actual theory of what we need. So another way of thinking about this is, so let's say I run my first stage regression. Well, here, let me keep these different. I think this will make a little more sense here. Oh. Oh. Scribbling things out here. Hold on. So I'm going to run this regression where I try to predict this X value I was interested in with my instrument. Okay. If I think about what would pi 1 be here, right? So I could think about, I'm running kind of this regression. I'm then going to come up with what are my predicted X values. So here my predicted X values would be whatever the prediction for that intercept is, prediction for that slope coefficient, and then this would be kind of times, what do I want here? Oh, sorry. This error term is up here. All right, so this is kind of be what my predictions for X would be. So if I'm then thinking about my kind of second stage, I've got the actual Y values. I want to predict that, but I'm going to use my predictions that came from my first stage. Okay. So I can think about here, what are my predictions going to be? Well, they're equal to this equation right here. Okay. So I can think about if I plug that in, and technically here, I've got my error term as well. So my predictions here are going to be something like this. Now, if I rearrange this a little bit, and I won't make you do this proof, but it would look something like this. So if I think about what is this equal to, I would have, we go back a ways, this is going to be the covariance between X and Z divided by the variance of Z. That was our kind of how we come up with that estimate for usually beta 1. Here it's pi 1. I'm just kind of using some different notation. Okay. So if I then kind of run this regression, I think about that's the value I have here. What I would then have, and I'm going to kind of ignore this for a second, it just essentially gets added into my constant. So I would have covariance of X and Z over the variance of Z times Z here. So if I then kind of run this regression, what do I end up with? Well, I end up with essentially this, right? The estimate for my beta 1 value is going to be the covariance of Y with Z over the variance of Z. So if I'm thinking about what I now have is this estimate is equal to covariance of Y with Z over the, oh, I left this out, sorry. I gotta plug this in down here. Covariance of X with Z over the variance of Z is equal to the covariance of Y with Z over the variance of Z. If I rearrange this equation a little bit, they've got the same denominator. I end up with my estimate from that second stage regression will be the covariance of Y with Z over the covariance of X with Z. You don't have to do any of this, right? This is just support as to why that running the first stage, using those predictions in the second stage, will end up with this result, which is that coefficient estimate we get from the second stage will be the covariance of Y with Z over the covariance of X with Z. Okay, so it's another way that we've come up with this. Now, instead of this a little bit easier, we don't have to kind of go through this theoretical or this kind of mathematical proof. It'll be kind of all baked into the values we see. Right? So what this is going to look like. Oh, do I have anything here? No, we're going to jump to our do file. Okay, I think this will help, and I'll kind of have some actual variables we can think about. So I've got, what I want, this IV health. So let me see. Oh, I'm going to go to open. I have my IV health file, so I'm going to open that up. I'll copy and paste this. Just in case I need to rerun anything. All right, this is kind of that path that I had. So here we'll say, this is the file I'm using. All right, in case I want to keep reading this. So I've got my IV health file opened up. I'm going to run a really naive regression. So we don't just have to do this with one variable X. I said can include additional controls, which makes it more likely our instrument is valid, right? That it's not going to be correlated with our error term. So here I'm trying to predict medical expenses, in fact, the natural log of them, using health insurance, the number of illnesses, age, and I believe the natural log of someone's income, okay? So I'm looking here and I think, okay, what could be a good instrument, right? Because if I run this regression, and I'm thinking about, all right, all of these kind of variables here, right? Whether or not I get health insurance is likely dependent on a lot of other things that would influence my medical expenses, right? If I have pre-existing conditions, right, maybe that's captured by illnesses, but I don't know, maybe I smoke, right? Well, if I'm a smoker, what is that likely going to do? It's going to make it less likely someone will give me health insurance, but that also is going to cause me to have things that make it more likely I have to have medical expenses, right? Or if I don't know, I'm let's think about like, I was watching the Indianapolis 500 is coming up, right? So if I'm a race car driver, do you think anybody wants to give me health insurance? I mean, there's a lot of, accidents. Probably not, right? And doing that makes it more likely I'm going to have an accident that I probably need to spend a lot of money on my house. So we have these omitted variables that we don't have data on that are likely to be causing a bias if we try to look at the effect of health insurance on medical expenses. Now, we know inherently having health insurance, is that going to increase or decrease my medical expenses? Well, if you have health insurance, you have in the hospital for 5 weeks, they pay for that. If you don't have health insurance, who pays for it? You do, right? Or you go bankrupt, right? So we know that there should be this relationship where if I have health insurance, my medical expenses out of pocket should be lower. So I need to find a good instrument. So I'm not sure if this is a great instrument, but here, the one that I kind of thought about from this data set was it has this variable for what the state's social security income was, right? So how much kind of they're giving you or how much the government is assisting you in terms of covering your medical expenses. So I'm going to use that as an instrument because if the state is giving me more money, am I more or less likely to go out and get private health insurance? If I'm getting more money from the state, do I have to worry about having private health insurance? No. So it should be related to that decision to get health insurance. So it meets that first criteria, which is that it's endogenous to X. This social security income ratio, or how much money the state is giving me, will influence my decision to get private health insurance or not. So that's my first stage. So I'm just going to run this regression. You can almost think about it here. And when I was writing this out in general terms, health insurance is the X variable I wanted to know the effect of. So remember, originally, I wanted to know the effect of health insurance on my medical expenses. Well, I've got some controls, but there's likely a lot of other omitted variables that I don't have. So my first stage is I try to find this instrument to predict X. So I'm trying to predict health insurance using that social security income ratio. I should have chosen a different variable because I can barely say this, right? So I'll go ahead, run this regression. Also, I should probably make these comments just in case I try to run these. Where I run that first stage and I see, okay, if I was trying to predict whether or not someone had health insurance, this is the 1-0 variable. So we'll start to get some practice and things that you might have to do in the detail. So how would I interpret that coefficient on my social security income ratio? Now, I think this ratio is like the percent of income, right? That they would, or percent of your income that they were giving you money for. So like a 1% increase would make it what, 0.19 decrease the probability to get private health insurance by negative 0.19. Okay. So we have kind of this 1-0 variable, so it's changes in the probability of that variable. Now, we're not going to focus as much on the interpretation, but notice if I'm thinking about, is that Social Security income ratio my instrument? Is it correlated with that X variable? What's one thing from this regression? So we said we want the covariance to be something other than 0. What's something in this regression that would support that my instrument is correlated with this X variable? So if I run a regression, what's the whole purpose of these coefficients? It's telling me whether or not there's a causal effect of the independent variable on my dependent variable. So what would I look at here to see whether or not that instrument is correlated with my X variable of health insurance? I would look at its coefficient. What about that coefficient? How can I say, is that coefficient different from 0? It's going to be a rough final. How can I tell you if a coefficient value is statistically significantly different from 0? I'm just looking at the p-value in the test statistic. So here I have a p-value of 0, which is telling me I can strongly reject that the relationship between this ratio and health insurance decision, I can reject that it's 0. It has some relationship. That's what I needed for that first criteria of my instrument. Now, that's just the first criteria. I can't get anything about the second criteria from these results. Okay, we'll talk about that later on. But from that first stage, one thing that tells me whether or not that was a good instrument is the statistical significance of that instrument. Okay. Now, assuming I don't have any other controls, what would be something else where a higher value would indicate that potentially this instrument was very explanatory about whether or not I got health insurance or my dependent variable? My R squared, right? Or adjusted R squared. The higher that is, the more variation I'm explaining in that dependent variable or health insurance. So we'll talk a little bit later on of how I can kind of figure out how high is high enough for that R squared. But for now, we'll kind of think about, we can really focus on just that statistical significance of the coefficient of that instrument. Is that making sense here in terms of the regression? Any questions on this? We'll make sure we get questions out of the way because we're going to walk before we can run here. So the second, stage, right, is I'm now going to have to use my predictions from that first stage. So even though I ran this regression, I need to run this command afterwards, which we've used this before. If I want to make predictions for my dependent variable after I run the regression, essentially what I would do is take those coefficient estimates, then for every observation, plug in their values for that variable, and I could predict the dependent variable. Well, we can't do that by hand for every observation. So the command we had stated that will do this for us is using that predict command. So after I run this regression, I'll use that predict command. I'm going to call this first stage. If it helps you, and I might do this in kind of later examples, I could call this, this is like my predicted values for that dependent variable of health insurance. Doesn't matter what we call it. We're just kind of giving it a name here. I called it first stage. If it helps you to think about, well, this is my health insurance prediction coming from my first stage, you could call it that. So I'm going to use this prediction. And I'm then going to put, so this is the predicted value of health insurance. In my second regression, I'm going to use all of the same controls in the original naive regression that I had that I know I had omitted variable bias in. But instead of using the actual X variable of health insurance, I'm using the predicted X value of health insurance. So just to kind of, so I have kind of multiple lines, if this is helping us with kind of this additional name. Right? I'm just replacing health insurance in my second stage with the predicted value of health insurance. Okay, that came from my first stage regression. Once I do this, so I'm going to go back and say, okay, what if we didn't use an instrument? My naive regression, it actually looks like having health insurance increases my medical expenses. Well, maybe, right? I mean, if I have health insurance, am I more or less likely to go to the doctor? More likely, which means I might incur additional medical expenses, right? But we also talked about this kind of, there's the omitted variables that might lead to this relationship being, flip the sign, make it smaller or larger. So instead of that naive regression, we're going to run our IV regression. In the second stage, we're using the predicted values for health insurance. So if I do that, the estimate on the effect of health insurance now is not positive. In fact, it is now negative. And I can say that it's statistically different from zero. So using this instrumental variable, I've eliminated all of the omitted variable bias that might have existed in my previous estimate. Okay? So I'm getting closer to that causal effect. I don't have all this bias in my coefficient from that second stage of regression. Okay. Any questions on this idea? So maybe if it helps just to kind of write out what we're doing in Stata here, since before I was kind of doing everything with hypothetical values. So what we're looking at here, if I was going to write this out, maybe I would ask you to do this on the exam, right? Write out what your first and second stage look like. So originally, and I'm going to shorthand this a little bit, but we wanted to predict expenses, and we wanted to use health insurance, and we had all of these additional controls, right? This was our Y variable. This was our X variable we were interested in. So what we're going to do with our first stage is we're instead going to try to predict our X variable using this instrument, which was that social security income ratio. And we include all of our additional controls in that first stage as well. So this was our instrument Z. We said what was a good indicator that covariance between health insurance and this social security income ratio was not equal to zero. Well, we just looked at that statistical significance of the coefficient associated with our instrument. So we were looking at before. And then the second step was, okay, from this regression, we're going to come up with the predicted values of X. Right? So we're running that first stage, saving our predicted values of that dependent variable from the first stage. And then we're going back to the original regression we wanted to run, but we knew we had omitted variable bias. And now I'm going to not include my X variable, but I'm going to include the predicted values of my X variable from the first stage, and then all of my additional controls. When I run this regression, I should now have a coefficient estimate, which eliminated my omitted variable bias or measurement error bias that might have been incorporated in that naive regressions coefficient. Okay, so just kind of just put some actual variables that match up with what we're doing in kind of that state of the file. Any questions here before we keep moving? Okay. Is this kind of clear what we're doing here? So we need two regressions, right? We save the predictions from our first regression and use them in our second. So there's some easier ways to do this in Stata, right? Which is instead of kind of running this line by line, I can use this IV regress command. So the format of this IV regress command is you tell it, I want to use this two-stage least squares. This is this two-part process. This is two-stage. I've been calling it first and second stage. You then tell it your Y variable. So for us, that was medical expenses. You then tell it the X variable. For us, that was health insurance. You then have to put an equal sign and tell it the instrument you wanted to use, social security income ratio. And then you can include additional controls, which we had here were like the number of pre-existing illnesses, age, and what their income was. So if I run this, I should get the exact same coefficient as if I break this down step by step. It's just doing all of that behind the scenes for me. So I run that regression, sure enough, I get the exact same coefficient estimate. Okay. Now, there's some things that the IV regress command does that we don't do if we do this by hand. Won't get there today. I might mention or talk about them a little bit more on Thursday. But we do get slightly different standard errors if we use that kind of built-in IV regress. It adjusts for some things that we haven't talked about yet. And to be completely honest, we're going to kind of hand wave over, right? So it's just more about knowing what that process is. It gives us that same coefficient value. If we use this built-in IV regress tool, there's some additional things that it does that we are kind of hand waving over that might impact our standard errors. But once we have this output, we can still say, okay, what is the effect of having health insurance now on medical expenses? It looks very different than that first naive regression where we didn't use an instrument. Okay. So any questions on this idea before we keep moving? So one downfall of this is, can I say whether or not this was a good instrument or that my instrument was correlated with the X variable? Well, how did I do that before? I looked at the results of my first stage. They're not here, right? If I use that built-in command. So what I can instead do, if I want to see those results, I just put a comma first here. And it shows me that first stage regression it ran and the second stage. Hopefully this is the exact same thing as when we did it. Oh, where did I do it before? Where's my first stage regression result? So I had medical expenses. Now I wanted health insurance. Oh, did I override it? Well, here it is, right? So that was my first stage coefficient. Compare that to what we found before, right? We kind of did it piece by piece. Gives me the same kind of results. The order is a little bit different of the variables. That's kind of a pain. But ultimately, it does all this work behind the scenes for me. I don't have to break this down line by line. So I can look at those first stage results. And what we said was, is that ratio variable correlated with health insurance, the X variable I was looking at? Yes, we said it had statistical significance. Okay, so it meets that first criteria. Now, I don't necessarily know if it meets the second criteria yet, because I need to know, was that instrument uncorrelated with the errors, right, in that prediction I was making for Y? So we haven't got to that part yet, but for now, right, I could just think about what's a very easy way I could do this. Well, we've found covariance matrices already. All I have to do is look at, well, what was the correlation? I could use the first stage results, but I could also just simply look at what is the correlation between medical expenses and that ratio. And then when I put covariance, it would tell me what that covariance is. Well, here it's something other than 0. All right, so that's good. That was our first condition. Now, when I look at the correlation of that instrument with whether or not, sorry, I flipped these. What do we actually want originally? We were looking at the instrument and the X variable here. So we found a covariance at something other than 0. Now, here's where my second stage might not be quite valid, because we said that second stage, what I need is that second condition. My instrument can't be correlated with the error term in Y. Now, this isn't a perfect way of looking at that, but is that instrument correlated with the actual Y values is a way we could say we can start to think about it. That's not quite right, because we need it to be uncorrelated with the error term. So here, when I look at this, okay, well, there is some correlation there. It's not exactly equal to 0. I might be concerned that that second condition isn't met. We'll talk, probably not today, but next class, how we can check that second condition. Now, one thing I wanted to point out here. So if we go back to our end result from that mathematical proof, we said the estimate that I see from my second stage, right, that coefficient estimate I see, should also be equal to the covariance between Y and Z divided by the covariance of X and Z. Okay. Well, what did we just find? So this was essentially our Y variable is medical expenses. Our instrument was this ratio. And down here, Z was our instrument. Health insurance was our X variable. Well, I have the covariance of Y and Z and the covariance of Z and X. If I just plug those in, I should get the same coefficient estimate, which if I take this ratio and put this into a calculator, you get negative 0.82. I should see the same estimate as I found from that second stage regression. Now it's a little bit off here. So instead of negative 0.82, it's negative 0.85. I was rounding those covariances to like the third or fourth decimal. I think it was the third decimal. That's going to cause, pretty significant rounding. If I take things out to the, whatever decimal, I would end up getting the exact same values, right? So the only discrepancy there is that I was rounding those covariances, to that fourth decimal, I guess. So I had like 4 and 5. Because there's so many trailing spaces here and these values are small, that is going to produce kind of a slight difference there. So why do this by hand? Well, I might ask you to do that on the exam, right? If I give you these covariance matrices, you know that the estimate you see from your second stage should simply be the covariance of your Y variable of the instrument over the covariance of your X variable of the instrument. But the rounding might cause slight differences here. Any questions before I keep pushing this a little bit further? Okay. So what if instead, and I'm going to save this just so I kind of have it in. So just kind of putting that comma first gave us like our additional first stage results there. Okay. Now, if I wanted to instead use a different instrument, so here, instead of using that state level Social Security income ratio, I was thinking about, I had something in here that measured like firm location. So this was something, I forget the exact data set. This was something like the number of medical facilities within a certain radius of where the individual lived. So if I live closer to medical, like if I'm living in Bloomington, I'm within driving distance, or an Uber will take me to a variety of different, orthopedic, right, doctor, eye doctor, et cetera, et cetera. If I live way out in like, I don't know, Nashville, Indiana, right? It's kind of out a ways from things. It's a trip for me to go in, to Bloomington to go to one of these offices. I might be less likely to go in. My medical expenses might vary. So here I'm thinking about, okay, maybe that firm location, right? Maybe the number of firms there, it might be correlated with this decision of, do I get health insurance or not? Because if I live far away, I'm less likely to go in. I'm not even going to go into the doctor. Why would I have health insurance? This is like when another good one might think about, like when I was younger, I didn't have health insurance, but I wasn't as concerned about needing to go to the doctor, right? So there's this kind of correlation where it's correlated with X here, but where firms locate, is that going to be correlated at all with medical expenses? Maybe, right? But maybe it's more based off of population, right? So maybe it's not correlated with that Y variable. Maybe it is, right? This is when we're thinking about good instruments. Sometimes before we get to the actual data proof, we just have to kind of think through the logic, right? And think through, could this be a good instrument? And then with some actual data, we can test to see whether or not it is. So here I'm going to run this regression where I, instead of using that ratio, I use firm location. I run that regression. And it looks like, oh, it's giving me quite a bit different of an estimate. I think before we had, what, negative 0.82. This is almost double in size and still statistically significant. So here I'm like, okay, maybe this was actually a better instrument, or at least it was eliminating or not eliminating different types of omitted variable bias than my Social Security income ratio was. Now, what would one way be to see, is this a stronger estimate? Or sorry, stronger instrument? If I look at the first stage results, right? So if I go back and look at the first stage results for that ratio variable, looks like it had a test statistic of negative 14. That firm location from our first stage, it has a test statistic of 7.19. So it is still statistically significant and correlated with that X variable But which instrument has a stronger correlation with health insurance? The one that has a higher test statistic. And I think they were like similar sizes of the coefficients as well there. So we can look at first stage regression results. This would still meet my criteria for a good instrument, but we could start to think about which one is maybe a better instrument. We'll have more pieces of the puzzle in class on Thursday. But for now, we're just trying to kind of focus on that first condition, right? Is my instrument correlated with that X variable that I'm using? I think I'm going to skip through this. We'll kind of save this, I think, for, and we jumped the gun here a little bit. I was looking at kind of that first stage. I'm going to work ahead a little bit. We're going to talk more about on Thursday's class. Do I have weak instruments? Kind of is that second criteria met? And we have a test for that. So this should be the last question on that problem set. Everything else you should be able to start tackling and answering after today. But this kind of last thing where we test that second condition using this endogeneity test, we haven't quite gotten there. And then I kind of already mentioned this, and I already showed you examples. You don't just have to have one X variable on that right-hand side. We can use additional controls as well, even if we're not focused on those estimates, right? Even if we're not focused on those coefficient estimates. So maybe giving you some better examples, I think will help solidify this idea. So I like this one. Let me see if there's another one I have that's better. Okay, we'll use this one. It's a pretty good example. So if I open up this data set, it's kind of wage 2. So I skip some of this stuff that we'll talk about next class. So I open up this free data. I think I've had it installed here. But I think you have to run this install. So no, it's SSC install and then kind of BQ. So this gets a bunch of free data sets. If you've already done this on your device, you shouldn't have to run this again. We'll open up this free wage 2 data set. I'm going to run this naive regression where I'm trying to predict wages. Right, that's my Y variable using education, experience, age, and marriage. So I'm really focused on what's the effect of getting another year of education on someone's wages. That's what I'm interested in. Well, I look at that coefficient and it's what, 72.3 and highly statistically significant. So I'm like, great. Tell people to go out and get a college education. It's going to increase your wages. And I was controlling for what? Years of experience, age, and whether or not they were married. Well, there's a lot of other things that matter in your wages. Maybe what sector did you find a job in? What major did you have? There's a lot of omitted variables that we don't have here. So if I can find a good instrument that is correlated with education, but not correlated with anything else that would help me predict wages. So not correlated with any of those other omitted variables. I could actually use that as an instrument and eliminate all of that omitted variable bias that comes from not just one other variable, but tons of other variables that I've omitted. So I'm going to think about maybe what's a good instrument is parental education, right? If your parents have a higher education, holding constant your education, should that make it any more or less likely you see increased wages? Well, I mean, it shouldn't, right? A company doesn't care if your dad has a college degree. If you don't, and you don't have the knowledge to do the job required, they're not going to hire you, right? When you send out your resumes, on your resume, do you put your parents' education level? No, they don't care about it, right? So in terms of kind of, is it correlated with wages or correlated with kind of the error term and predict? We would think probably not, right? So this is where we kind of have to use our best kind of guess before we look at the actual data. But then is your parents' education level correlated with whether or not you have higher education? I mean, we can look at any data set. Hey, they want the cost themselves. They can help you navigate it. They're more likely to have higher wages. They're more likely to be able to afford to help you attend college. So your parents' education level should be impacting whether or not you end up getting higher years of education as well, right? So it looks like that instrument of parental education will be correlated with our X variable, but it should be uncorrelated with wages. Now, I understand there's like networking, right? And maybe that, gives you a leg up. But for right now, we'll assume like companies are actually making the correct decision, which is if you don't have the knowledge, you don't have the education level that makes you good at this job, they're not going to want to hire you, okay? So we'll come down here and we're going to run this 2-stage regression. Now, I'm going to do it by hand here in a second. Here, we'll just use the built-in tool, right? So I use this IV regress command. I tell it I'm running this two-stage least squares regression. I want to predict wages using education, and I'm going to instrument using, here I just had father's education, but we can think about this as parental education. Okay? And then I had those additional controls. I put in comma first here so we can see the first stage results as well. So I go ahead and run that. So I look up here. Here's my first stage results where I was predicting the individual's education using their father's education, that instrument. Does this look like it's a good instrument? Well, is it correlated? Is the father's education correlated with the individual's education? At any statistically significant level, yes, that p-value is 0. So we have that first criteria met strongly from our first stage. Second criteria, once again, we'll focus on that next class, whether or not that's met. So if I then look at my kind of second stage results, I get a coefficient of 142, which compared to when I didn't use an instrument, it was only 72. I found the effect of another year of education was more than double what it was when I had that coefficient that included the omitted variable bias. So it can dramatically change that estimate we see, or dramatically change the suggestions that we would make in terms of policy to workers, right? It nearly doubled that returns to education, which I would hope all of you are concerned with what the returns to education are as you're thinking about going out into the job market, right? So these are actual practical things that we would want to be able to estimate. If I'm a university, I'd be able to tell you in my brochures how much you can expect starting salary, right? Based off of having 4 years of a college degree or 4 years of additional education at my institution. Okay? So that's kind of more of the practical application we're thinking about. Here, I can break this down into steps. So this is where we want to get kind of good at writing this out in terms of what our first and second stage are. So I've got it in the stated code here. But once again, I would probably expect you to do something like this on the exam. Have the exam written. So what we're trying to do is think about, I'm trying to predict wage, and I want to know what is the impact of an additional year of education, and I've got a bunch of additional controls. So what I'll do if I'm using an instrument is I'll have my first stage where I try to predict that X variable of education, and I'm going to do so using my instrument Z. Right here, that was our kind of father's years of education. And I have all of my additional controls in that first stage as well. What I'm then going to do is save my predictions from that first stage. And in my second stage, I'm going to go back to what I originally was interested in, which was the effect of education on wages. But instead of using the person's actual education, I'm going to use their predicted number of years of education based off of that instrument and the additional controls. Okay. And so here's all of my additional controls here. So just to make this point, what I don't include in my second stage is the instrument. So what I would not include in this second stage, my controls were like age, married, I forget the other one that we used. We would not include our instrument, right, in that second stage. We were just using it to make those predictions that we put into our second stage. Any questions on this idea before we keep moving? Okay. So sometimes maybe as you're working on this problem set, it helps to kind of write out what you're doing, right, with these variables. So we can break this down into steps instead of relying on that kind of built-in tool. So our first stage was we were trying to predict that X variable with all of our controls and our instrument. So when I run that regression, I should end up seeing the same code, right? I've got my first stage here from the built-in tool. Here I just ran the first stage. I get the same estimate on that instrument. Okay. I then am going to save my predictions. So here I call them my predicted values for education using that predict command after I run that regression from the first stage. I'm then going to run my second stage, which is I'm trying to predict wages, but now instead of using the actual X values, I use these predictions from my first stage. Okay. what I should hopefully end up with is the exact same estimate, 142, as we found using the built-in tool. Sure enough, I do. Okay. So that's how you would kind of break it down into steps, right? And we can kind of look at, comparing it to that built-in tool. It gives us the same results. Any questions here before we keep moving? So just to reiterate, and so this is something we'll kind of focus on a little bit more next class. Let me see here. So I'll add something in here. Oops. So I said another way we can calculate this coefficient is it should be equal to the covariance of y with z. So for us, that was the covariance of education with, y was what we're looking at, wages, with father's education, our instrument, divided by the covariance of our x variable with that instrument. Right? Well, I can find these values. So there we go. Nope, that's not the command. The command is correlate. And then we add on the n, we want the covariance. And then I'm just going to copy paste this. The other thing we wanted was the covariance of that instrument with the x variable. So if I look here, no, I don't need this display command, sorry. That's for what I want to do next. So I run these. I think, okay, that covariance of y with the instrument is what? 318.3 approximately. And the covariance of the x variable with that instrument is what? 3.161, right? I guess I'll keep this out to the third decimal. So what we wanted to get what that coefficient is the covariance of y with our instrument. So this is what? 318.305. And divide that by the covariance of the x variable with the instrument, which was what? 3.161. So if I do that, I get about 100.69. So this is where, if I'm using these kind of values rounded to the third decimal, I am going to find something that's a little bit off, right? 100.67 instead of 142. Oh, well, actually, what this also doesn't do is what does this not account for? Maybe. So when I was setting this up before, all I had on that right-hand side was just the x variable. So the only way I can actually use this correlation ratio is if I don't include any additional controls. Okay. So the only way that kind of using this method would work is if I use those covariances, but I don't have any additional controls in my first, second stage regressions. Okay. So this is great for a very naive kind of approach where I was trying to just use one variable and instrument it. Oh, okay. There I am getting the exact same value. All right. So, we can use this method. I might ask you to do this on the exam, but what I would have to do is give you a model where we don't include any additional controls. That's the only way kind of taking that ratio of the covariances would produce the exact same coefficient as my second stage, right? Or my kind of two-stage least squares. Okay. But I could ask you to do that, right? Give you a very simple model. Maybe I don't give you the regression output. I just give you this covariance matrix, and you could find what that coefficient should be. Does that make sense what I'm saying there? Okay, I'm adding this into what was in the do file. So here, I'll save it so I make sure we have this next class, and I'll kind of repost this that kind of includes what we've added during class on Canvas. Okay. Oh, what else do I want here? Got what? A little bit of time left here. So I said we might get out of here early today. So let's see here. Let me get the time added in here. So I think I had it set to be the end of class. So I don't remember what the code is today. I think it's 32 something, but I might have changed it. never mind. It's 19.87, right? So 19.87 will be the code that kind of gets us in there for the day. It should be under the main page on Canvas now. So is everybody seeing that? Anyone getting in, having trouble getting in there? We're good? So 19.87, 19.87. We're good? All right, so let's think about these kind of two questions, right? And we'll kind of allude to what we're going to talk about next class that we didn't quite get to today. So this is going back to we started out this discussion, and what we want to remember, these two criteria for a good instrument is. So if it's a valid instrument, we said it should be correlated with what? So if it's a good instrument, we need it to be correlated with our independent, our right-hand side, or our X variable. The variable we want to know the coefficient estimate of. We don't have any coefficient estimate on Y, right? It's what's always on our left-hand side. So maybe if you want to remember it this way, the instrument needs to be correlated with the variable that we want to know the effect of on Y, or the variable X that has that coefficient beta 1 associated with it. So we want it to be correlated with that X variable. What is our right-hand side or our X variable? That is our independent variable. That's the thing that's changing. So we want it to be correlated with X or correlated with that independent variable. What we don't want it to be correlated with, and once again, this isn't quite technically correct, for the sake of what we're doing in this class, we're going to think of it this way. We don't want it to be correlated with Y. What is Y? Y is our dependent variable. So we want it to be correlated with X or our independent variable, and we want it to be uncorrelated with Y. Now I said technically, it's not that it's uncorrelated with Y, it's that it's uncorrelated with not with actual values of Y. So think about it this way. So if I've got Y, I usually kind of think about, I'm trying to predict it using X. But my actual Y values also include some error, right? So when I'm making predictions for Y, I'm using these X values. This isn't quite technically correct, but it's like, I want the covariance of my instrument with Y conditioned on X to be equal to 0. Well, if I'm conditioning on X, really the only thing left in Y is the error term. So I said you can think of it as though it's uncorrelated with Y, but what we're really saying is because to predict Y, we are controlling for X. If it's not correlated with Y, we've already kind of holding X constant, it's really that the instrument is uncorrelated with the error term in Y. But the question, I kind of phrased it more like what I would, kind of think when we set up today, we're just thinking about, is it just uncorrelated with that Y or that dependent variable? Once we get to kind of working through material next class and doing review for the exam, what you actually need to say for that second criteria is not that it's uncorrelated with Y. You need to tell me that it's uncorrelated with the error term. Okay, that error term that we would kind of need to look at the actual Y values. Is that clear what I'm saying there? Okay. So we've got the answers hopefully to one if we've been paying attention here, right? So we said it's going to be correlated with the independent or the X variable, uncorrelated with our Y or our dependent variable. Okay. Now, we talked about one thing we can use to tell whether or not that first criteria is met. Is it correlated with our X or our independent variable? Was looking at the statistical significance of our first stage results, right? So if we're looking at the statistical significance from that first stage result, that's telling us, did the instrument have an impact on our X variable? Right, that was our first stage. We tried to predict that X variable using our instrument Z. So we looked at that in some of the output and we said, oh yeah, in all of our examples, it was highly statistically significant. Well, what would it be statistically significant at the 99% level? Our Z value that we would kind of compare to would be about what, 2.58, I think is the 99% level. So there, if we see a test statistic that's greater than 2.58 from that coefficient of our first stage result, that's a good indicator that that first criteria is met, that our instrument is actually correlated with X. Now, we didn't quite get there, but I alluded to it. What did we say another statistic from that first stage would be a good indicator that my instrument is good at predicting X? If it could explain more of the variation, what would that be? The, well, F statistic, but first R squared. So there's a test that we won't kind of go through explicitly, but essentially we could compare that R squared to basically 0, whether or not it's any different from 0. That wouldn't come, we know the R squared has to be positive. So we talked about the F distribution a long time ago. We always know that it has to be positive. We'll always have a positive test statistic. So when we're kind of testing to see is that R squared different from 0, that would be an F statistic. When we were looking at that output from our first stage results, we always have this F statistic here. And that's associated with, is our R squared different from 0? Okay. So another good indicator of whether or not our instrument is correlated with X is if that R squared is really high. What tells us that is a specific, how high is high enough? It's 0.3 R squared, 0.4. We would base it not just based off the R squared, but the sample size that we had. And so that is kind of all going to be baked into our F statistic. And really our rule of thumb for these instrumental variable regressions is any F statistic greater than 10 is a second indicator that we have that this is a good instrument in terms of that first criteria. Okay? So if we go back and look at all of our earlier examples, right, was father's education, if we looked at that, where was it at? We wanted our first stage here. We said it is statistically significant, right? The estimate of father's education with education, but it also has an F way greater than 10, 109, right? So those would be kind of the two pieces of evidence that we could use, the statistical significance of the coefficient on the instrument and that F statistic associated with the R squared from our first stage. If I then go all the way back to looking at our earlier example, where did I have? Here we go. Of firm location, right? Using it as an instrument for health insurance. Well, there we said it's statistically significant at every level. And once again, my F statistic way greater than 10. So all these examples we kind of looked at today, all of these are going to indicate the same thing, which is that these are good instruments. I chose them for a reason, right? Now, what can happen, and I think I'll have a couple examples up on Thursday's class, is sometimes those two things don't always align. Sometimes the statistical significance of my coefficient might suggest that it's a good or a bad instrument, while my F statistic would suggest the opposite. It would have to be things that are kind of like right on the cutoff, right? So we'll have some examples of that next class. But in terms of the quiz, right, what we want is an F statistic greater than 10. And then the statistical significance, that p-value would be 0, but essentially, our kind of last cutoff for a test statistic would be the 99% level. So a p-value of 0.01 or a test statistic greater than 2.58 in absolute value. Okay. So greater than 2.58 and then greater than 10 will be kind of our two indicators there. That first criteria is met. So I think I had that set to be due at 2, so in class. So make sure you're getting that submitted before you leave. Once again, you should be able to work through the vast majority of that sixth and final problem set with the exception of like the last question. That's what we'll kind of look at on Thursday's class. I imagine we'll just look at the first half. I'm sorry, the first half of class will be new material, new examples, and then we'll start doing some review in that second half. Okay? All right. Enjoy this nice weather. I will see you guys on Thursday.